Welcome to lecture. We'll get started in just a minute, continuing on in chapter 14. That's where I think we left off. So we'll continue on there. And again, a couple of reminders that we will be taking the quiz later after lectures. They'll be open starting around 12 our lab time. You can go take it at that point. Again, through Canvas, like we've done the exam and some other things as well. So we'll get started here in just a second, continuing on with chapter 14, and then we'll probably roll into chapter 15. Like always, if you have any questions, feel free to ask them at any time during the chat box there. And again, I will get to your questions if you do have them. So we'll talk about all that stuff. We'll take a couple moments right now to talk about sort of what's happening in terms of lab and then also the quiz. So like I said, the quiz will open up around 12 o'clock for you to take it. Again, just like last time, you'll take it up online on Canvas. Once you've submitted your quiz, you'll need to upload your work just like you did for the exam. And you know, for those questions that do have obviously work associated with it. So trying to think off the top of my head, I'm not sure if all the questions have work associated with it, but just like the exam, the questions will be labeled as to just like the exam, there will just be you know, questions that are labeled that says make sure you show work for those. And obviously, like always, when you show the work, make sure that you show all the units, the setup, the answer as well, the right sig figs and all that kind of stuff. Again, remember online, if you're submitting an answer that is a number, just submit the number. And remember, I don't think you'll have any of these on this particular quiz, but again, if you enter a number into Canvas and it automatically changes it for you, it should be okay. If you enter something in scientific notation, which again, I don't think you'll have to do on this quiz, you know, it's use that the little E button to do that. But I don't think you'll have to do any of that kind of stuff. But again, if it does change your answer, when you do enter it, it's okay. Just make sure on your work that you show obviously the correct answer to the right digits and stuff like that. Yeah, I think that is correct for chapter 14. It is pretty much what we're talking about now. It's not a very long chapter, so it's just that this portion that we're talking about here from chapter 14 is what you are responsible for. So again, that quiz will be open about 12. You go take it. In addition to the quiz, there is a lab for today, and again, it is experiment 19, I believe, and 19, which is precipitation reactions. So it's a lot of writing molecular equations, total ionic equations, and net ionic equations like we talked about. Don't even remember what chapter that was in, but it was a little bit ago. I think it's chapter 7 is where we talked about that, if I'm not mistaken. 7 seems like the right number. So I think you got about 45 minutes to take the quiz. It's about 20 points, I think. Experiment 19, I'm going to make is due tomorrow. So give you a little extra time because you're going to use some of the time, obviously, for lab to take the quiz and stuff like that. So experiment 19 will be due tomorrow, I think around 12 or something like that. So I'll give you an extra sort of day to do it since we're kind of doing the quiz as well during lab. The quiz will open at 12 o'clock. So as soon as we're done lecturing, I won't say exactly at 12, but hopefully, you know, as soon as we're done lecturing, you know, the quiz will be open for you to take. And then once you're done with that, you can also find on Canvas, you'll be able to find experiment 19, and you could go off and obviously do that. And experiment 19 again will be due tomorrow by like 12, stuff like that. So the quiz will be just like normal, you know, 3-4 questions, just like a quiz we've taken before. So it'll be just like a normal sort of quiz. Again, you'll just have to show the work like we did on the exam, and make sure that you obviously upload the work within the appropriate amount of time after you submit your exam, okay, or your quiz. Again, there's different versions of the quiz like normal. You'll have to do the same sort of process as you did for the exam. So you'll have to sign the academic honesty agreement for the quiz, and then that will open up the quiz for you to take. Once you take the quiz, it will then open up the assignment where you could upload your work. So just like you did with the exam, you'll just have to go through that module. There'll be a module that says obviously taking quiz 3, I think it is, and you'll go through that module just like you did for the exam. So you have to do it in order, just like in the exam. You have to obviously read the academic honesty agreement, electronically sign it if you want, or you can print it out and sign it. And then that will open up the quiz. You'll answer your 3-4 questions. And then once you've submitted it, you then can, the assignment for you to upload your work will be open at that point, and you could go do that. Just like before, you want to make sure you're ready to take the quiz. Just like the exam, once you start, you can't stop, right? The timer keeps going, even if you click away. If for some reason you do click away and you need to find it again, you could go back to the module section and obviously find everything that you need, you know, to finish the quiz. You'll be given a periodic table. The periodic table is at the very beginning of the quiz. It is there as a picture. It is also there as a PDF file in case you cannot see the picture. So you can just click on it, and then it will open up a periodic table for you to use in case you can't actually see the picture. I know sometimes people have a little difficulty with that. So other than periodic table, I don't think you need any other type of conversion factors or anything like that. So that should be probably all that you need for this quiz. Any questions on the quiz or anything like that? Like I said, there is technically a lab for today, which is experiment 19, which will also be available after lecture. I'll post that up there. So once you're done with your quiz, you could go do that. To answer your question, yes, I'm going to open a second meeting for lab. So whenever, if you finish your quiz or in enough time or something like that, and you want to come in and ask some questions about, you know, the lab or something like that, you can. But obviously, you could spend that time taking your quiz would probably be best. And if you do have questions, you could always email me, you know, if you have questions on the lab or something like that. But I think the lab should be pretty straightforward. If you have any questions in terms of how to do any of that, you really could reference your notes from, again, I want to say chapter 7, wherever we talked about double displacement reactions, types of reactions, it'll be in that chapter. Is where all that stuff is. You basically just have to watch the video. And again, for the lab, you're only going to write the reactions for anyone that made a precipitate. So some of the reactions will not make a precipitate. And there's basically, when you look at the lab, there's 2 tables. There's one that's I'll just write it here. There's one that's a reaction work or something like that. And that's where you can write your molecular equation, your total ionic equation, work it all out, and your net ionic equation. And then there will be one last table at the very end of the experiment, which says something like, I don't know, I think it might say reaction table. And in the reaction table, the only thing that you need to write is the net ionic equation. So what you would have here, so you just pretty much need to copy over the net ionic equation, again, for only the ones where you actually saw something occur. Again, if there was no reaction, you don't have to write the reaction table or anything like that. So that's pretty much the lab. It is pretty straightforward. There's no real calculations or anything. It's just writing the balanced equations and the net ionic equation and the total ionic equation. Any questions on any of that stuff there? Okay. So then let us continue on lecturing here. So we were talking about intermolecular forces last time. And intermolecular forces are the forces that hold one molecule together with another. So like what we have on the screen here, these two water molecules are basically held together through an intermolecular force. And they're held together because the hydrogen part of water is more positive because it's polar molecule. The oxygen side of water is more negative. So it's really that opposites attraction between the positive and negative that holds these two molecules together. And that really is the basis of all intermolecular forces. It is that electrostatic attraction between something that is sort of positively charged and something that's negatively charged. And that is ultimately what all those different types of intermolecular forces are. We talked about three types. We talked about hydrogen bonding. We talked about dipole. We also talked about dispersion forces. And hydrogen bonding is usually the one for polar molecules that have a bond between hydrogen and nitrogen, oxygen, or fluorine. So like what we have here, we have hydrogen that is bonded to an oxygen. And what that does is it typically will create a separation of charge and create sort of a positive side, negative side to that bond. And that allows that interaction to occur. And this is hydrogen bonding. This is the intermolecular force that is used by water. This bond right here is hydrogen bonding. And it is the strongest bond. It is the strongest bond that we see here between everybody. And in terms of intermolecular forces, we're having a little bit of trouble. Give me 1 second. Let me try. I don't know. Again, sometimes it gets a little crazy. Give me 1 second. Let me just try something and see if this helps. If not, try to adjust it on your side as well. All right, let's see if maybe that's better. I'm not sure, but we just kind of have to work with it as technology, right? So hopefully. All right. So the hydrogen bonding is the strongest of all that intermolecular forces, and it is the one that will happen when we have a polar molecule that has the ability to hydrogen bond. So this is the one where the polar molecules come together, but they do have that ability to hydrogen bond. Dipole-dipole interaction is also between polar molecules. The difference is it is between polar molecules that do not have the ability to hydrogen bond. So they are the ones that do not have that ability to actually hydrogen bond. They will also work okay because they essentially are polar. So they will have a positive side and a negative side to the molecule, and a positive side and negative side. Where they're able to interact with each other is through the positive side of one and the negative side of another. So dipole-dipole is used for molecules that are polar, interacting with other molecules that are polar that lack the ability to hydrogen bond. while hydrogen bonding is for polar molecules that have the ability to hydrogen bond. And the last type of interaction that we talked about is dispersion forces. And dispersion forces are really for our nonpolar guys. And they are the way nonpolar molecules are able to interact with other nonpolar molecules. Really, everybody could use some type of dispersion forces, but it is truly the main force that nonpolar guys could do. It is the weakest out of all of them because in order for them to interact with each other, they gain these temporary positive and negative charges that occur. So this is just a summary of sort of everything that we talked about sort of last time. And again, what we were just talking about, that dipole-dipole interaction is the one that occurs with our polar molecules, again, that do not have the ability to hydrogen bond, while our hydrogen bonding is for polar molecules that has the ability to hydrogen bond. Remember that just because a molecule has hydrogen in it does not mean it has the ability to hydrogen bond. It does need to be a bond between hydrogen and nitrogen, oxygen, or fluorine. So it does not always mean that they will have the ability to hydrogen bond. If you see hydrogens like what we saw with CH4, for example, CH4, if you looked at it, has a ton of hydrogens, got 4 hydrogens, but because the bond between carbon and hydrogen is nonpolar, it does not have the ability to hydrogen bond. You kind of need that polar aspect of it to do that. Dispersion forces are sometimes called London dispersion forces, sometimes called van der Waals forces, all these interactions. But dispersion forces are the weakest of all 3 intermolecular forces, again, because they're kind of temporary forces that occur. And as soon as those electrons, for example, move around, they will break apart sort of their interaction and form new ones. So in terms of strength, hydrogen bonding is the strongest, the next strongest dipole-dipole, and the weakest out of all of them is that London dispersion forces. Now, these are all intermolecular forces, which are the forces that hold together, like we talked about, 2 molecules together. And they are always weaker than an intramolecular force. An intramolecular force is the force that holds an individual molecule together. Thus, things like ionic bonding is intramolecular, covalent bonding is intramolecular. Those are always stronger than your intermolecular forces. Any questions on that there? So here's just some pictures of that. These are dipole-dipoles. Again, what makes something sort of different in terms of dipole-dipole and dispersion forces is the fact that if a molecule is polar, like what you have in a dipole-dipole interaction, what that means is no matter what happens to that molecule, there's always going to be a side that's going to be positive, more positive, and there's always going to be a side that's going to be more negative. So that will never change, which means that's why it's relatively strong, because they just need to get near each other. And that's different than a dispersion force where they normally do not have a charge, but do gain these temporary charges. So they have to kind of wait for that temporary charge to occur in order for them to interact. And that's what, again, why dispersion forces are weaker than our dipole-dipole. They also will, when you get a whole bunch of molecules together, like what we have over here, they will try to align themselves in a way where they maximize the attractive forces. So they kind of maximize getting the positive sides of everybody near the negative sides, and minimize the repulsion forces, which is when we get, no matter what you do, there's always going to be a situation where you're going to have sort of a positive side near a positive side, which doesn't really want to be near each other. You may all have a negative side near a negative side of a molecule, get near each other. And they really try to minimize that and maximize the areas where they can sort of opposites attract. This is hydrogen bonding happening here, again, between our oxygen and our hydrogens. So this is, again, the force that happens with polar molecules that do have that ability to hydrogen bond. And because water is a polar molecule, no matter what happens, this side of the molecule is always going to be positive. It will never change. And this side where the oxygen in will be more negative. It also will never change. So it will always be basically fixed. This is our kind of dispersion forces, which is sometimes what is referred to as an instantaneous dipole. Instantaneous means it normally doesn't have a charge, but in this particular case, all the electrons perhaps went over to this side. And when it does, it will gain this temporary negative charge here. This guy will gain a temporary positive charge. And what that's going to cause is all the electrons in this guy to start to head this way, away from that positive charge. So this second atom, which normally would not have a charge either, will now also gain a negative charge on this side and a positive charge on this side. And then this gives them a temporary way to sort of align themselves and have a way to interact with each other through the positive side in one and the negative side in another. And again, this is sort of dispersion forces. This is very weak. Because as soon as these electrons decide to kind of come back around and move around to another more even distribution, that molecule will then lose that partial charge and it will kind of break apart. And, but this guy will still have that partial charge and kind of have a new interaction it could have, and it sort of continues that way. So that's why these dispersion forces are relatively weak, because they're temporary. And as soon as those interactions kind of break, they can't really maintain interactions between different atoms, as opposed to something that's dipole-dipole. Over the long haul, they're able to keep that interaction happening really well. Any questions on intermolecular forces? Okay. So obviously you do need to know the three different types of intermolecular forces. You need to be able to determine what is the main intermolecular force for a particular molecule. And really that's going to be tied into molecular geometry and molecular polarity. Again, if you can figure out the polarity of a molecule, it helps you a lot to figure out, will it do hydrogen bonding? Will it do dipole-dipole, or will it do dispersion forces? So the last thing we're going to talk about in this chapter is evaporation and vapor pressure. So vaporization or evaporation occurs obviously when liquids escape, our molecules escape the liquid phase and go into the gas phase. It requires a lot of energy to overcome those intermolecular forces. So remember, if you have something like water, it is that interaction here that will break, right, to separate those water molecules, say from the liquid phase to get into the gas phase. And once you break that, that will give you steam that's flying around, or gas molecules. When something goes into the gas phase, it occurs at its normal boiling point. So for example, water at 100 degrees Celsius is its normal boiling point. Condensation is the opposite process. It's the process where those gas molecules basically drop back down into the liquid part. So when you have a liquid, and at the surface of this liquid, you basically have both of these processes occurring kind of at the same time. You have some escaping into the gas phase. You have some escaping into the liquid phase, and going back and forth. So at the surface, this of a liquid, this always occurs. And in a situation, there is sort of a buildup of pressure that occurs with a gas above the liquid portion. And that really is what is known as the vapor pressure. The vapor pressure is the presence the pressure associated by that vapor at equilibrium with its liquid. So liquids that have high vapor pressures are said to be volatile. They can evaporate really rapidly. So in order to have a high vapor pressure, that would imply that you need to have a lot of gas molecules. And in order to have a lot of gas molecules, that would mean that you are evaporating that liquid very quickly. The vapor pressure of a liquid is given by the temperature and determined by the intermolecular forces. The stronger the intermolecular forces, the lower the vapor pressure, because it won't be able to overcome those intermolecular forces and go into the gas phase. So we sometimes will see this, for example, if we look at a liquid that's in a container such as what we have here, and in a closed container, if we put a liquid in there to begin with, like what we got over here on the left-hand side, once you put that liquid in that container, the rate of evaporation, which is what we're seeing here, will probably be a lot higher. And in a closed container such as this, those gas molecules have no way to escape. So once they get up here, there really is no way for them to basically escape. So they will eventually start working their way kind of back down. And as they work their way back down, some of them will go back into the liquid, while some of them will still be coming out of the liquid. And at some point, this will reach what is known as equilibrium. Very badly written, equilibrium. But basically what it means when we say it reaches equilibrium is just as fast as those guys are coming out of solution into the gas phase, they are just as fast dropping back into solution. So essentially nothing changes. And typically what you'll see if you kind of look in comparison is you'll eventually see the liquid level kind of go down a little bit once it reaches equilibrium. And again, there will be kind of no further change, but you will see a slight decrease in that liquid volume once it does reach equilibrium. The vapor pressure in this mixture here will be caused by all these gas molecules that it's above the liquid causing pressure. So if you have a greater amount of gas molecules above the liquid, you would have a higher vapor pressure. If you have less gas molecules above the liquid part, you would have a lower vapor pressure. This is also why, for example, this process is occurring all the time. So if we had like a puddle, for example, of water, and if we had a puddle of water, the rate of evaporation would start to occur all around this, right? Guys would be jumping out into the gas phase. Right, just says liquid. Now, when you have, say, water in an open area, you will get some of these guys coming back. But what will happen, though, is because the air is there, it will push a lot of these sort of, and it's able to evaporate because as the rate of evaporation occurs, the air kind of pushes those gas molecules away. It prevents them from coming back into that little pile of liquid that you have. And usually, right, the water will sort of evaporate relatively quickly, depending on how much you have. You just have like a little bit of wetness or something on the counter that will eventually sort of evaporate. And that's because the rate of evaporation will be greater than the rate of condensation. And again, a lot of that's contributed to the air as they kind of push those molecules away from the liquid, doesn't allow them to come back. And that's also why if you take a liquid like in a cup, for example, yeah, well, the air itself will kind of blow those away. So for example, let's just say we had this is water in the liquid state. So as these water molecules would naturally start to go through evaporation and start to escape, you have your water in the gas phase. the air will push these water molecules kind of away, and essentially these water molecules are no longer available to come back in. So they can't come back in to that liquid water and keep the liquid there. So eventually what essentially happens is you get a greater rate of evaporation, and the air kind of pushes those molecules away. And then at some point, you don't have very much, if anything, coming back into the liquid portion. Because again, at the surface of any liquid, no matter where it is, you constantly have, guys jumping to the gas phase, and you also have guys going back into the liquid phase. So at the surface of any liquid, no matter where it is, in what container, at the surface, you've got that constant exchange that's occurring. And in sort of open air area, the air kind of pushes away those molecules and doesn't allow them to come back into the liquid portion. So you get, again, that greater rate of evaporation until eventually that kind of puddle evaporates away. That's also why when we're talking about kind of over here, if you have like a liquid in a container, a big liquid in a container here, it too also, if you put it in a cup, essentially start to evaporate. But the evaporation rate is a lot slower, right? Before that would completely evaporate. And that's because there's less surface area as well, right? And the puddle like this, where it's spread out, you have pretty much everybody all the way around it free to go through evaporation. And here, all these water molecules in a cup, they gotta kind of just work their way straight up. There's not as much area evaporating at once. So although evaporation is continuing, and the same process would occur in like an open cup of water, it would occur a lot slower because, again, it's not occurring kind of 360 degrees, if you want to think about it, as it would if, the entire liquid area was open to the air. Any questions on that there? Okay, so if I'm not mistaken, that should be it for this chapter, I think. Yes, it is. Okay, so that was the end of chapter 14. We're going to go to 15, so just give me a second to get that going. And again, a reminder that our exam is 1 week from today, and chapter 14 has been moved off of it. So it will only go to chapter 13, stuff like that. Let's see here. Let's find the right one to click on here. Try that one. Okay. All right. All right, so chapter 15, which will be on exam 4, I guess that would be. We're down to 15, 16, and I think 17. 3 more chapters. We're all out of material. That's good, I guess. Chapter 15 is solutions. So we're going to talk about solutions, talk about how solutions sort of dissolve in each other, what things make solutions. We're also going to talk about concentration of solutions, how to calculate concentrations, and so forth. So let us get going on this. So really a solution, when we talk about solutions, again, is those guys that have that aqueous symbol. Oh, I guess I should get something to write with there. So it is our guys that have that AQ symbol that's there. And remember that the aqueous symbol is different than liquid, as the aqueous means that you basically made a solution, which typically means you took something that's solid and you dissolved it in something like water to actually make a solution. And that is different than, again, just the L, which is a liquid. A liquid is a pure substance. So like if you just had water, H2O by itself, nothing else mixed in there. That's why, again, water is considered L, a liquid. while something like sodium chloride solution is considered aqueous, because to make it, you took some solid sodium chloride and you melted it, you dissolved it in water. And a lot of important chemical reactions, biological reactions take place in this aqueous environment, which essentially means a water environment usually. Now, an important part about a solution is there's actually two parts to a solution. A solution is actually made up of the solute, and the solute is the smaller part of the solution. So in our example of the sodium chloride solution, it would be the solid sodium chloride, or the sodium chloride part, not necessarily the solid. The sodium chloride part would be the solute, while water would be the other part of that solution, and that is what is known as the solvent. So the solvent is the larger part of the solution. So when you make a solution, it is made up of those two things. It's made up of a solute and a solvent. Yeah? And both of those things together, again, is what makes up a solution. So how do you know what is the solute versus the solvent when you see something like a formula written like any of these formulas here: sodium chloride solution, hydrochloric acid, sodium nitrate? The solute is always the name of the solution. So if somebody says you have a sodium chloride solution, that means the solute is the sodium chloride. If you have a sodium nitrate solution, the solute would be the sodium nitrate. Hydrochloric acid, hydrochloric acid would be it, but really hydrogen chloride would be the solute in that particular case. And probably 9 times out of 10, if you see the aqueous or you're talking about a solution, a lot of times the solvent is water. We're going to talk about why that is in just a second, but it does not always have to be water. So you can use different things as solvents, and there may be different solvents used because of certain situations where water would not be a great solvent. So although a lot of times water is a very kind of universal solvent that is used, it's not always 100% always the solvent that's used. Again, there's a lot of things where water would be kind of a terrible solvent in a solution. And we'll talk about why that is in this chapter as well. So 2 parts of the solution: we have our solute and our solvent. So as I mentioned, water is a very good solvent, and it's a very good solvent for a lot of things. And that is, again, because water is polar. So as we've been talking about before in previous chapters, including the last one, water basically has 2 sides. It has a side that is more positive, which is where the hydrogens are, and it has a side that's more negative, where the oxygen is. And again, a reminder that that is all based on the idea that water is a polar molecule and has overall a molecularly polar molecule, and overall has an unequal distribution of those electrons in it. And it allows it to have sort of a fixed side that's positive and a fixed side that's negative. So when we think about water as being a really good solvent, it is a very good solvent for things, as we will see, that is ionic, because really ionic compounds are positive and negative guys, and also other polar molecules, which also has a positive and negative side to it. So that's why water works really well with these guys, because ultimately it's able to interact well, because water itself has a positive and negative side. Ionic things are positive, negatively charged. Polar things also have positive, negative sides. It gives them a way to use those intermolecular forces, like we were talking about in the previous chapter, to interact with each other and help things dissolve. So when we take something like sodium chloride and we dissolve it in water, because sodium chloride is a strong electrolyte, it will 100% break apart into sodium ions with a +1 charge and chloride ions with a -1 charge. And that works extremely well with water, because water will be able to surround those guys. And that is, again, that process of hydration is when water basically will surround these ions. And it does, again, a couple of things. This would be our sodium, for example. This would be our chloride over here. And what happens is, because the sodium is positively charged, it will be surrounded by the oxygen side of water. Again, the oxygen side of water is negative. So it's able to interact with it through the intermolecular force of the negative side of water and the positive side of that ion. Opposite is true when we take our chloride ion and it goes to dissolve. Because chloride is negatively charged, it will interact with the positive side of water, which is our hydrogen side, and allow basically water to surround both of those ions. That does essentially two things. The first thing it does is it allows water to dissolve. So to us, when we look at it, it looks like, wow, water disappeared. It's gone. It's completely like disappeared. And it really didn't disappear. It basically just got mixed into all the water molecules that are in there. And to our sort of naked eye, we can't visually see it anymore as it's gone. As it gets mixed into all those water molecules, they pretty much engulf each of those ions. And to us, it appears like it disappeared, but it really just dissolved, obviously. And it's still there. We just can't visually see it at that point. Water also, in this case, helps prevent the two ions from coming back together, because there is such an attractive force between the positive sodium ion and the negative chloride ion. That force of attraction is that intramolecular force. That's a super strong force, which if the waters were not there, they would just automatically, like a magnet, kind of come back together. And we actually do see this happen, as we've done before when we took early on in the semester, those early ones where we lit the Bunsen burner, we had those solutions in the evaporating dish and we evaporated off the water. Once we get the water out of the way, like if you did put this up on an evaporating dish and heated it up, all the water molecules would start to evaporate and they would go into the gas phase. And at some point, once we start evaporating off all these water molecules that are here, there will at some point be nothing in between the sodium ion and the chloride ion, as all those water molecules basically have evaporated away. And at that point, they are definitely going to want to come back together, and they would come back together as that solid sodium chloride. And if you remember back to those early experiments that we did, when you looked in your evaporating dish, after you did that, after you put your evaporating dish on that thing of water, what you had left in your dish was sort of this solid residue. And that solid residue would be, for example, the sodium chloride coming back together after you evaporated off the water, because there's nothing to prevent them from being apart at that point. As the water earlier, when they were dissolved, basically prevented them from, kind of coming back together. So sort of the process where water works as a solvent here is sort of what we see on the screen. And really what we see on the screen is really what is represented when we write aqueous. So really when we have sodium ions there, it's really sodium ions with a bunch of waters attached to it. But we don't really write those in formulas like that. That's why, we use the aqueous symbol to sort of represent that. So really when you see the aqueous symbol, it's really representing that if it's an ionic compound, those ions are really surrounded by water in there. And although we talk about in solution, it's really just the sodium ions floating around freely. Truly, they're not necessarily floating around freely. They do have water associated with them as they're in their ionic form, floating around in that solution. Any questions on that? And this is sort of the process where we dissolve something like sodium chloride. sodium chloride, for example, which is an ionic solid. All ionic solids pretty much line up like this in these kind of big clumps, if you will, where they're held together by that intramolecular forces, the positive and negative attractions. And basically, some water molecules come in and they start plucking off those ions. And as they pluck off those ions, they start to surround them, like we see up here in the right, and also on the bottom here. And that helps this solid sodium chloride basically dissolve. Now, if you put something that's solid in water and you just kind of put it in there, this process would occur kind of like what we see in the picture, but it would probably take a little bit longer. And when we do dissolve something, we typically do what? We typically perhaps grab something and start stirring it. So a lot of times we'll grab something and start stirring it. It does two things when you do that. Obviously, it creates a lot more energy as you're stirring. It also will throw a lot of water molecules all over this guy a lot quicker. And that's going to help the rate of it dissolving by obviously providing more water molecules over a greater surface area. So as we kind of stir it, we kind of help it along in the dissolving process rather than waiting for each of these water molecules to sort of come in and kind of pluck off each of these ions. So these different types of bonds, again, are kind of important in terms of how things interact with each other. A reminder that ionic bonds, as we talked about many times at this point, are bonds between a metal and a non-metal. Again, there's no sharing of electrons that occurs there. There is that really strong electrostatic attraction that occurs between the positive ion and the negative ion. While covalent bonds, as we talked about, is some aspect of sharing of electrons that occur. And those sharing of electrons could be equal, which would give you a nonpolar covalent bond. Those sharing of electrons could be unequal, which will give you a polar covalent bond, but there's some aspect of sharing. And depending on the types of bonds that are involved, will kind of have an effect on how things interact with each other, whether they're able to perhaps do some hydrogen bonding, when they're able to do dipole-dipole interaction, whether they're able to maybe not do either of those things and do something like dispersion forces. And that's just a reminder, we sort of talked about that. That was just about electronegativity, so don't worry about it. You should hopefully know that. So let's talk about some examples of things that are soluble in water. So really in water, which is polar, anything that's ionic will be soluble. So again, if you take something that's like sodium chloride, you take something like ammonium nitrate, which are ionic compounds, they will be very soluble in water. Really what happens is a type of intermolecular force, which is sometimes called ion dipole interaction. It really is still kind of under the dipole interaction. But sometimes people will call this ion dipole, and it's what we saw earlier on the last slide, where basically our ion is surrounded by water, again, the negative side of water in this case, and so forth. It's called sometimes ion dipole because it involves an ion and a polar molecule, and that's where sometimes people will call this sort of a ion dipole interaction. Again, it's an intermolecular force like we were talking about in the last chapter, and it's sort of under the big category of still like a dipole-dipole interaction. But some people will specifically call it an ion dipole sort of interaction. And that's basically what we saw, that these guys, when they go for a swim, will break apart into ions and basically get surrounded by water. And again, when that process, as the water is surrounding it, is essentially what allows it to basically dissolve and make things soluble. There's also other substances like sugar that we know that if we take sugar and we put it in water, it is also soluble in water. Ethanol as well is soluble in water. And these are not ionic compounds. These are guys that contains carbons, hydrogens, and oxygens. And these are guys that will basically be doing covalent bonding. So instead of ionic bonding, like we have in our ionic compounds, these guys will be doing some type of covalent bonding. So what allows something like sugar to be soluble in water and something like ethanol, which basically ethanol looks like this. If my pen doesn't go too crazy right now, give it a try here. So ethanol looks something like this. And what each of these things sort of have in common that allows them to sort of interact really well with water is they contain a bond that actually looks very much like what you see in water. And it's really this OH bond here. This OH bond, although this entire side of the molecule is pretty much nonpolar, this bond over here between the oxygen and the hydrogen is a polar bond. So the oxygen is more negative, the hydrogen is more positive there, again, based on electronegativity. And what that does is it gives it a place to interact with water because, again, water also is polar like we've seen. And the negative side of this oxygen here in water is able to interact with the positive side of that OH bond in ethanol, and it allows them to interact really well with each other. So we'll see a picture of sugar in just a second, but although sugar is a larger molecule, it also is littered with a bunch of these OH groups. And everywhere there's an OH group on something like sugar, it gives it an opportunity to interact well with water through the process that we were talking about in the last chapter. You should hopefully recognize that process of that bond between hydrogen and oxygen. That is what is known again as hydrogen bonding. That is hydrogen bonding that's occurring that allows those two different molecules basically to interact with each other. And here's a picture of that. This is not ethanol, this is methanol. But methanol also has, although this part of it is nonpolar, this guy is more negative on that OH group. This guy is more positive. And again, it's able to interact with the positive side of water and also the negative side of water, like we see down here. So again, these interactions between these two different molecules, one being water, one being methanol, they're able to still interact with each other through those intermolecular forces like we were talking about in the previous chapter, also hydrogen bonding here. And again, these are these intermolecular forces that allows them to interact well with each other. So if you took something like methanol and you put it in water, and if these were both, for example, solutions, when you would put them in, they say, the same test tube, it would look just like one liquid was in there. So remember that when two liquids sort of mix really well, a lot of times we don't talk about it in terms of solubility. You could, but sometimes it's referred to as being miscible with each other. And if two liquids don't mix, that's when you'll see different layers occur that's insoluble with each other. And sometimes in terms of liquids, people call it immiscible. IMMISCIBLE. Here is ethanol, and again, you can see ethanol here participating with hydrogen bonding. So when we talk about these sort of intermolecular forces, you could have something like water interacting with itself, so like two water molecules within itself, and the intermolecular force it would have between water and water is hydrogen bonding. You could also see in these last two examples as well that you could have two different molecules. So something like water and something like ethanol, which is what's on the screen right now, they also can interact with each other through intermolecular forces. And in this case, they also will be using hydrogen bonding to do so. Any questions on that? Now, again, not all things will be soluble in each other. And if we take a very good example of that is oil. When we talk about oil, oil pretty much is nothing but a long chain of carbons and hydrogens that are bonded together. So it's just a long chain of a carbon attached to a carbon, attached to a carbon, all attached to like hydrogens. That's not double bonded. That's a very badly drawn single bond. But what we do know about the two types of bonds that we do see in something like oil is the electronegativity of carbon is 2.5. The electronegativity of hydrogen is 2.1. Again, when we do the difference, that gives us our 0.4. And the bond between carbon and hydrogen is considered a nonpolar bond, which means there is no separation of charge. It's sort of neutral. The other bonds that we see in oil is the carbon-carbon bond, which also would have an electronegativity value difference of 0, which means that's a pure covalent bond. So when we get something like oil, we have nothing but nonpolar bonds. It's a nonpolar molecule. It has no way to interact well with water over a long period of time. And typically what we see with oil is it typically will end up floating on top of the water. And that is because oil is insoluble with water. That's because when these two guys get together, the water molecules here are going to try to use hydrogen bonding. Our oil molecules will try to use, since it is nonpolar, like we talked about in the last chapter, nonpolar is essentially dispersion forces. So what we have here when these two guys try to come together is we have water that wants to use hydrogen bonding. We have dispersion forces in oil, and that's what it wants to use. And those two forces are not compatible to work over a long period of time. For a short period of time, they can interact with each other, and that's because essentially everybody can do some type of dispersion forces. So some type of dispersion forces pretty much can happen for any type of molecule, nonpolar, polar, they could do a little bit. But really over the long period of time, water wants to use hydrogen bonding, oil wants to use dispersion forces. They cannot interact with each other. They can over a short period of time. So if you take oil and water, or like say oil and vinegar sort of salad dressing, right? If you mix it, it'll stay mixed for a little bit. But eventually what will happen is, right, everybody will separate out from each other. And that's because over that long period of time, the oil, for example, has no way to continuously interact with water to keep a mix. Again, they can do it for kind of a short period of time, but over the long period of time, they just have no way to keep those attractions from happening. So that's like something like oil, vinegar, salad dressing. You can mix it, it's nice, you put it on your salad, you put the bottle down. Over a long period of time, everybody starts to sort of separate out from each other. Typically, when we do get something that is organic or oil, something like that, and something that's water, usually water will end up on the bottom, or the organic guy like oil will end up on sort of the top layer. It's very similar to, if you remember the experiment we did in person that involved the halogens, and we all went to the fume hood, and on the top layer either changed color, the bottom layer changed color, and we had those two different layers. And that was because in that experiment, we put hexane, which is pretty much all carbons and hydrogens, non-polar, and we mix it with basically a water solution, and we had sort of that top layer and bottom layer. They're able to separate out from each other because they have no way to interact well with each other. So this brings up an important sort of understanding when we think about solubility and how things behave with each other. It is this guy right down here. It is this idea of like dissolves like. So things that have similar intermolecular forces are ways to interact with each other through similar intermolecular forces. They typically will be soluble in each other. Things that do not have that way to interact with each other through similar intermolecular forces will typically be insoluble in each other. So what that means is if you have something that is, again, if you have something that is polar, that interacts with something with polar, it's all good. They both are going to use dipole-dipole interactions. If you have something that is ionic, interacting with something that's polar, they also will do some type of dipole-dipole interaction, so they're all good. If you have actually something that is nonpolar, that interacts with something that is nonpolar, they also will be good because they both will be using dispersion forces. So all these sort of interactions is our like dissolves like. These are all going to typically be soluble in each other. It is only when you cross over and you mix something that is polar and non each other. So the idea of like dissolves like is a very important sort of idea in terms of solubility. So this is where we're talking about if we had something that was non-polar, for example, if we had something like oil, we would not want to use water as a solvent because it will not mix because they have no way to interact with each other. So if we had something like, we had something say like, do Br2. Br2 is a non-polar molecule. Because it's a non-polar molecule, it would want to use dispersion forces for how it's able to interact with something. So if you try to put Br2 in water, they will not mix because water is polar and it wants to use dipole-dipole. Now, if you take Br2 and put it in something like CCl4, carbon tetrachloride, if you look at carbon tetrachloride and do sort of the molecular geometry on this, this is a symmetrical molecule and has everything attached on the outside's the same. This is going to be a non-polar molecule. And something like carbon tetrachloride here would be a good solvent for Br2 because Br2 is non-polar. It's going to want to try to use dispersion forces. Carbon tetrachloride is also nonpolar, so it's going to use dispersion forces, and that is your like dissolves like. So those two things would interact really well for each other. Again, opposite if you try to take the bromine, the Br2, and put it with water, because they are going to do the bottom right there, polar and nonpolar, which is not going to allow them to interact really well with each other over a long period of time. Any questions on that? So here's a couple of pictures. Up on top is sugar, although it is a relatively large molecule. Everywhere you see an OH group, that gives it a place to interact with water through hydrogen bonding. And although it's very large, it is littered all the way through the entire molecule with those OH groups. And because that OH group works really well with water, that's what makes something like sugar soluble in water. On the bottom is typically what you see in oil. And again, you can see that is pretty much all carbons together, which are nonpolar. Carbon and hydrogen bonds also, which are nonpolar. So our oil on the bottom there is going to try to use dispersion forces where our water would not. So although it also is a very large molecule, it has no way to interact. So it will not interact well with water. While this guy up on top, although he is a large molecule, again, everywhere we see these OH groups, gives it an opportunity to interact with water, which again is our polar molecule through hydrogen bonding. So again, able to kind of hydrogen bond all the way around to each of these guys. And this is typically what we see when we do mix oil and water together. We get that sort of separation that occurs. And again, the oil usually will end up on top. The water will end up on the bottom, and not a lot of interaction happening between them. Again, over the long period of time, kind of like the salad dressing example, everybody will sort of separate back out from each other because they have no way to maintain those interactions over that long period of time. So when we talk about solubility, a couple of things about that. When one substance essentially will dissolve in another, when the solute will dissolve in the solvent, it is said to be soluble, and that will typically make a solution. So again, if you took something like sodium chloride and you dissolved it in water, you'll get a sodium chloride solution. If one substance does not dissolve in another, it's said to be insoluble. So this, for example, is like those solubility rules. When we mix a couple of ions together, some are insoluble, some are soluble. So sometimes you will get a solid that will form. So for example, something like oil is insoluble in water, like we talked about. There is a limit to the solubility of one substance in another, and it is based on temperature. So for example, if you took sugar, which is soluble in water, and you dump a couple of sugar packets in, you know, it will dissolve. Maybe you ordered some dinner, you're waiting for it to come. At the table, you take all the sugar packets and you dissolve it in the water. Eventually, at some point, the sugar may stop dissolving if you pour a ton of sugar in there. And there is a limit to really how much you could dissolve a solid in a liquid, and it is based on temperature. So typically, if you increase the temperature, provides more energy and so forth, and it allows the solvent to take more solid in. If you decrease the temperature, usually you can get less of that solid to dissolve in the liquid part. There are some things that are always soluble in each other. So gases are always soluble in each other, and gases are always soluble in each other because they are essentially constantly flying around. So as they are constantly flying around in the same container, they are constantly passing each other, and they are constantly mixing with each other. So gases are said to be soluble in each other always, just by the nature of them flying around. They're constantly doing the mixing. Some liquids are also mutually soluble in each other. So things that are polar and polar will be soluble in each other, like we talked about. Things that are non-polar and non-polar will also be soluble in each other, just like we talked about a little bit earlier. And again, that brings up the idea of, like we talked about, this idea of like dissolves like. So really the basis of that is anything that has similar ways to interact with each other should be soluble in each other. And usually what we're talking about is those intermolecular forces. So the solubility of a solute in a solvent is dependent on the temperature. At higher temperatures, we typically will have a larger solubility of a solid in a liquid. Again, when we increase the temperature, we're adding more energy. That's going to allow more of that solid basically to break apart and enter into the liquid phase. At a lower temperature, we have a larger solubility of a liquid, of a gas in a liquid. So what that means is, if you remember from our gases, if we have a liquid and we have a gas molecule in it, at a lower temperature, our gas molecule is flying around a lot slower, which means as it's flying around slower at that lower temperature, it's going to be dissolved in the liquid part for a lot longer period of time, as opposed to if we raise the temperature, this gas molecule would just shoot way out of the thing, break through the glass apparently. But it would be moving a lot faster, which means obviously you could get through the liquid part faster, but at a lower temperature, that gas will be sort of dissolved in that liquid part for a longer period of time. In terms of gases, the solubility also depends on pressure. The higher the pressure, the larger the solubility. So if you remember about pressure and volume, the higher the pressure, the smaller the volume. So the smaller the volume, that means that those gas molecules are now flying around in a smaller area, which means just by that by them being in this smaller area, they will also be mixing a lot more. So higher pressure, smaller volume, more mixture of those gas molecules as they're flying around. Now, there's a couple different ways that we can describe a solution. So let's talk about those. And we can describe it by how much solute is dissolved in a solvent. So the first way that sometimes a solution is described is it's described as a saturated solution. And a saturated solution contains a large amount of solute. And basically what that means is if you've hit a saturated solution, you have hit the point where no more solid will dissolve. So pretty much all of the solid at that given temperature, because it is temperature dependent, will dissolve in that solvent. No more solute will dissolve. So if you take more solid and you try to dissolve it, once you hit a saturated solution, the solid will not continue to dissolve. It basically will pile up on the bottom and it will no longer be able to dissolve. The opposite of that is an unsaturated solution. And in an unsaturated solution, you have not hit that point yet. So in an unsaturated solution, at that particular temperature, you still have room or the ability to dissolve more solid, and you will continue to dissolve solid until you hit the saturation point and a saturated solution. So when we have a unsaturated solution, it will continue to dissolve that solid until you hit a saturated solution. Really badly spelled saturated solution. Sorry about that. Pen is not behaving today. And we'll get this saturated solution that will occur. So unsaturated, you haven't hit that point yet. You could still continue to dissolve the solute, the solid, if you will. And then at some point you will hit that saturated solution. And it's at that point, no more solid will dissolve. It again will just sort of start to pile up on you. Now, there's another way to describe another type of solution, which is known as a supersaturated solution. And in a supersaturated solution, you have too much solute dissolved. In the solvent. So basically, one way that you can make a supersaturated solution is to make a saturated solution, which is basically your maximum amount of solid that you can get to dissolve in there. You could heat it up, which will then allow you to dissolve more. It will also evaporate off a little bit of the solvent. And then what you typically do is after you kind of dissolve more at the higher temperature is you take that solution and you let it cool back down. When that solution cools back down, essentially what has happened is it cools back down. All that solid is still dissolved at that point. But what you ended up doing is creating now a solution that ended up having way too much of that solid or solute dissolved in that solvent. Because say at 100 degrees Celsius, you could dissolve 40 grams. But when you let it cool back down, say to 25 degrees Celsius, it should only be able to dissolve like 20 grams. I'm just making these numbers up, by the way. So what you end up with, though, is a solution that now at 25 degrees Celsius has 40 grams dissolved in it, which is way too much for 25 degrees Celsius. And what you create basically is an unstable kind of solution a lot of times. And if you look at that solution, if you're very, very careful, when it cools, say, back down to that 25 degrees in my example, after we've dissolved all that stuff, it will look just like a solution, but it is very unstable. It is so unstable that if you just kind of knock it a little bit, breathe on it too much or something like that, are just take like that much, that little dot right there of whatever you dissolved in it. And if you put that into here, it will cause pretty much all of that solid to start to come out of solution. And you'll actually see it like this. It'll start like there's all solution, and then all of a sudden, once you kind of tip it in that scale, either knock it, add a little bit of what you dissolved in it, it will eventually, and you will end up with basically a rock hard solid that was a solution just a second ago. And that's because, again, you created really this sort of unstable solution where by the process of what you did, you were able to get all this solid to dissolve. But when you cooled it back down, that's like way too much for it to have dissolved. So it creates this really unstable solution. And it recognizes that as soon as you maybe knock it, as soon as you add one little speck, and it will cause all of it to come out of solution. So that's a super saturated solution. I'll try to find maybe for next time a little demonstration of that. So just to finish up today, two other ways to describe a solution. One is a concentrated solution. And in a concentrated solution, that is one where you have a lot of solute dissolved. So sometimes in the lab, we see a lot of the bottles, they have this big M, which we'll talk about in this chapter, which is molarity. And that is what is known as the concentration of that particular substance. And when that number is a large number, like 12, 18, 16 molar, that means it is very, very concentrated. Typically, what we use in the laboratory or in experiments is one like the second one, which is a dilute solution. So typically, they take these solutions, which are really concentrated, and they add something like water to it, and it dilutes it down. So in the case of a dilute solution, you have more solvent, perhaps, and a smaller amount of solute. So the concentration will come down and it's dilute. It's kind of like the example if you get like a big glass or big cup of soda or something like that, a big gulp from say 7-Eleven before you come to class with all the ice in it, and you drink it, it tastes really good. It's nice and concentrated. After class, you get back to your car, all the ice is melted. Obviously, when all that ice melts, it's going to dilute down the soda, and you go taste it. It doesn't taste as strong as it did before. It's definitely more dilute in that case. So a concentrated solution is one that contains a relatively large amount of solute. A dilute solution contains a relatively small amount. I think that's a good place to stop for today's lecture. Any questions on anything we were talking about? So like I said, we are into 15, and I think we only got 16 and 17 left to go in terms of chapters. So we're in the home stretch here. So make sure you keep on top of everything, studying and all that. So again, 1 week from today should be exam number 3, I believe that is. And again, just like exam 2, we'll take it on Canvas, just like we did exam 2. The quiz will open up shortly, in about 10 minutes or so. As soon as we're done here, I'll kind of click everything open. Again, you could go take the quiz. It's basically formatted very similar to how you had to do the exam. So there'll be an entire module that will be the quiz. You again need to do each of those things in order, which just like the exam, you need to read the honesty policy. You need to sign the honesty policy. That then will open the quiz. And just like our normal quiz, it's maybe 3 or 4 questions. You can answer the quiz. Just like the exam, do not hit the submit button until you have answered everything. So just like the exam, make sure that you wait and until you've answered everything before you submit the exam. Once you submit the exam, then you could go back to the module section, and you should be able to open up the assignment to upload your work like you had to do with the exam. I'll get to your questions all in just 1 second. You could open up the assignment to upload your work, which again needs to be anything in terms of units, all the setup, the correct answer. You, just like the exam, you have to answer every question on there. So let me just give me a second to look at your questions. Yeah, so chapter 14 is not going to be on the exam next week. So I haven't had a chance yet, but I will go up and adjust chapter 14's due date for the homework. The quiz, you could start the quiz at 12 o'clock. I think you got maybe until like 2:30 to take it. Again, a reminder that just like the exam, if you start right before the due date time, it will only give you like 5 minutes. Yeah. So make sure you start with enough time so that you get the full 45 minutes. And again, if you start around 12-ish or so, you should again have plenty of time to finish it. Just like normal, it will cut you off, obviously, if you start like right before the due date or the end of availability date. So if you start in the 12-ish area, not exactly at 12, you don't have to, but in that area, you should have enough time to finish it. Let me see that. Yeah, I think it's like 2:30 it closes, but again, don't start at 2:15 or you just get 15 minutes. Yeah, so again, just like before, when you enter any number answer, any number answer in the box, no units, but do make sure that you show units on that. I believe the submission time is 2:30, I believe. I'll double check, but I think it is. Yeah, so again, you should be able to hopefully knock it out. And again, just make sure that you start with at least 45 minutes before 2:30. Otherwise, it will cut you off with not all your time and all that. Again, if you kind of start around our normal time, you should probably be okay. And like normal, I think everything's pretty self-explanatory on the quiz. So I'll have my email if you need to email me like you kind of did on the exam, but I don't really think there will be any sort of necessary need for that. There is a periodic table that will be, I think, the first sort of question area that is a picture. And again, if you can't see that picture, there's a PDF file in there that you could click on and open and use and stuff like that for a periodic table, which I think is the only thing that you need. The other thing I would say, there are some balancing equations as we talked about. So make sure you do follow the instructions. So if a coefficient is 1, when you balance the equation, don't leave it blank. Do put 1 into the box and stuff like that when you do it, okay? And also, like I said, there is experiment 19 today. It will be due tomorrow. So when you're done with your quiz, you could go watch the video. I think it's only 6 minutes or so, and you can work on finishing that. And again, if you want sort of a reference point for the experiment, I think it's out of the chapter where we talked about different types of reactions, which I think is chapter 7. I could be wrong, but I think it's that chapter. So you could look at that to sort of figure out how to do that if you don't remember, or look back in your notes. I will take a little break. I will open up the lab session until about our normal time, but I would probably recommend go take the quiz now and then kind of work through the experiment when you're done with it. And like I said, you could always email me if it's outside that lab period and stuff like that. Any questions on anything else? Okay. Good luck on your quiz and all that good stuff. Remember, make sure you're ready to start. Before you start it, you got your paper to write your work and a calculator, because again, once you start, you cannot stop the clock, okay? Have a good rest of your day. We'll see you next week if I don't see you later.